This problem is an example of the operational amplifier and the non-ideal characteristics and how to analyze an operational amplifier given such imperfections such as the voltage offset, the slew rate, so this is the slew rate, the gain bandwidth product, which is also known as the unity gain, and then this is the large signal limitations of an amplifier. So this is your configuration with the 9K and the 1K feedback resistance. So if you were to analyze this to find the value of the ideal gain, you will note that this is a inverting amplifier, which means that your gain, which is VO over VN, is negative 9K over 1K. So your ideal gain would be negative 9 volts per volt would be the gain. This is the inversion, so the gain part of it would be 9 volts per volt. If you were to look at, so this is 9 volts per volt is the ideal gain of this. If you were to look at amplifier 1, so looking at this amplifier 1 and its characteristics, what would be the bandwidth of this circuit if you know that the input Vn is 0.1 sine omega t? So the bandwidth needs to have the consideration of the two effects of the slew rate and the gain bandwidth product, or the unity gain value that you're given on a data sheet. In this case, we're given the gain bandwidth product. This is the same value as a unity gain. So to find that, first looking at unity gain, you would take the value of 2 megahertz and divide that by the gain of this plus 1, and the plus 1 part comes because it is an inverting amplifier. If you find the gain for a non-inverting amplifier, you would use that. So in this case, it's 2 meg over 10. So this value gives you 200 kilohertz. For the slew rate, the effect of the gain or the bandwidth would be, you need to choose which one is going to give you the worst case. For slew rate, the lower value is going to be the limiting one, because that means that it's going to be a lower frequency and therefore limit the bandwidth of the amplifier configuration. So you would use 0.5, and you need to make sure to use the microseconds. So that would be 0.5 over 1 times 10 to the minus 6, and then you multiply that 1 over 2 pi, and then you would take the gain times the input would be your peak value, and this gives 88,419 hertz. So since this is the lower value, you would say that this is the bandwidth of the circuit for these considerations. If I was to use amplifier 2 instead, or amplifier 3, and only consider the gain bandwidth product, you can see here that at 65 megahertz, if I'm only looking at the unity gain, this would give me a larger possibility for the bandwidth if I did not include the slew rate in that. Another question is if I still have that same input of Vn is equal to 0.1 sine omega t, what would be the maximum and minimum values seen at the output considering the voltage offset? So again, I want to look at the worst case I would see from this effect. And in this case, that voltage offset shifts up the DC portion at my output. So I would want to use the higher value for this one, which would be 1.7 millivolts would be my max value for that. And that offset, due to that, would be 1.7, and the gain plus 1. Again, it looks like it's on the inverting. Even though I have my input on the inverting terminal, this always looks like it's on the non-inverting one. So I have to use the non-inverting gain part of that, which would be 9 plus 1. So this gives me an offset of 17 millivolts. And my ideal gain would be, output from that would be 0.1 times 9 sine omega t. So I have 0.9 sine omega t. So my max would be 0.9 plus 17 milli. So I get 0.917 millivolts. And my minimum is going to be 17 milli minus the 0.9. These are not millivolts, these are volts. In volts. So this would be the maximum and minimum I would see due to the voltage offset error. Another question about the non-ideal effects are which amplifier gives you certain characteristics. So which one gives you the lowest error? And the lowest error is going to be due to the internal gain that you have for the amplifier. The ideal characteristic is going to be the one that gives you the largest value. So that would give you the least amount of error when you have the more ideal characteristics. So amp 2 in that case. If I want to know the one that gives us the lowest DC offset, the lowest DC offset is going to be the one with the voltage offset value being the lowest, so that's going to be amp 1. And the one that gives you the largest gain, largest bandwidth possible is going to be the one with the largest gain bandwidth product, so amp 3 would be that amplifier that would give you that characteristic. Another question is how to modify this circuit without removing any resistances but adding in a resistance to minimize what's called the input bias current. And to do that, you would add in a resistor, and it needs to be the equivalent resistance that's seen at this node. So that would be 1K in parallel with 9K, which equals 900 ohms. So you would put a resistor of 900 ohms in at this terminal, and that would eliminate the effect of the input bias current. So this concludes the majority of the questions that you'll see for the non-ideal effects